Okay, so today I will be talking to you about the research project I'm doing here at the University of Houston and give you some insight about how you can take or undertake research in application of Internet of Things for smart building and smart cities. And hopefully we can spark some discussion and ideas that can move the research forward. So today I'm going to talk about the motivation, why I'm thinking about this concept of living building, and I'm going to describe the system in terms of data acquisition, storage, and processing, and then talk about the fundamental challenges and what we can do as researchers. So, as we know, there is a lot of work going on in smart cities, and basically we're implementing sensors everywhere, from the cameras to motion sensors to weather sensors, and there is a lot of data available now that can enable us to improve our infrastructure in terms of resiliency, improve issues related to mobility in terms of congestion, improve the life of the citizen in going to agencies and do the business, and even improving energy efficiency. So those are the challenges that we are faced with as a society. And other challenges comes from the concept of smart grid, where now we're would like to make the smart grid as reliable as possible. So there are services provided by utilities. Given all the infrastructure that we're implementing to progress the economy, we're consuming more energy as we grow, and there is a need for energy efficiency. So we all know the problem of energy and how we should save, basically, to improve our energy demand and reliance on it. So the concept of living building is, the idea is that if we are going to implement sensors and those buildings are being now monitored and they communicate with us, can we make them autonomous in terms of energy efficiency, in terms of making our environment comfortable and healthy, as if these buildings are a living organism. And the reason, because we have now what we call building energy management system that is monitoring what's going on, and then the building manager automates certain things in the building, but it does not. They don't take real-time action, and they have to wait for complaints or somebody to call them and tell them that something is wrong. So that's this concept of living organism. There are some write-up going on the slide. I'm not sure. Yeah. So that concept of building brings us to solve issues that are basically optimization issues. And when we talk about optimization issues, then we are optimizing the energy or optimizing the utilization of a microgrid. We're taking a context information and making system context aware. And this is what the previous keynote speaker talked about. And solving that optimization could be done through either static optimization, or could be done through dynamic optimization. For instance, when we do classical optimization techniques, that brings us to doing an offline data analytics, and requires basically a human to go and do the offline and then come back and adjust the system. So when we do Internet of Things, basically we enable this what we call online optimization or real-time optimization. We enable the intelligence to be implemented at the building level, and we want to improve the reliability of those buildings. So by using Internet of Things, we're moving basically from a classical optimization technique to now what we call AI-based optimization that enable us to take real-time action. So what I'm showing here is really a typical layered model showing collection of data. So on the top, we have different channels that we take the data from, videos and social media and mobile. We could have sensors as well. And we say that we change that data, or we store that data in a certain cloud, and then we do what we call real-time optimization engines using AI and stuff like that. So this is just a generic model. I'm going to show some specific applications later on. So if we're talking about living building, then there are certain components that we need to implement. One of them is the nervous system. Our nervous system enables us to take action, to make us move and transfer the information. So in terms of living building, a nervous system would be the network, the wireless, the 5G, and all the technologies around it. So that will play a key role in smart building or living building. There is the concept of regulatory, where we regulate our own behavior, and that comes to what we call the building control. And then there is, in our case as human, we have an immune system. That means our system will take action in defending ourselves and maybe recover. And we do go to doctors just when that's problem we cannot solve it. So similarly, we should design this environment, living building or smart city, as fault tolerant as possible. And obviously, you won't be able to design a system that is completely fault tolerant, but at least it can handle certain level of failure. And then you call in that building manager, or that's, between quote, doctor, who can fix the building from time to time. So what is now the role of Internet of Things? So this intelligent building functionality will be basically enabled by Internet of Things, because we need the data, and we need data, and we need it reliably, and it has to be communicated through this wireless sensor network or other wireless network. And this is implemented as a layered services. I think the layered services is a key concept that we have to kind of utilize. Otherwise, we're gonna have a system that is very complicated. This is an example of the physical layer. So we have a certain physical layer already deployed in terms of building, in terms of energy, renewable energy, storage, etc. Now, on top of that building, or on top of that physical layer, we are going to implement certain other layers like sensors and that are taking data from the energy sources. And then we have the other top layer, which is information processing layer. So note that I'm dividing here things in broader concepts. So if we're looking at the information processing, we're looking at TCP/IP and all that 7 layer that comes on top of it. But if we're looking at the energy, so we're looking at overlaying and renewable energy on top of whatever we have in the infrastructure, like buildings. So from from a single building scenario, this is a scenario that we implemented at the University of Houston as a small prototype. So we have appliances and we have that are connected through a wireless network, and then we take the data and store it in the server, and then we could access through a smartphone or laptop or communicate with the system. This is a typical data acquisition system with sensors, communication, storage, and then processing. Now, if we are going to talk about connected building and living building, they should communicate and make a smart decision. And each node here can represent a building, and you could tell that now we have this wireless communication that could be done through 5G or LTE or Zigbee, depending on the environment. And then that's neighborhood or that's network communicate again with the server, similar to what we presented. In terms of TCP/IP, if we now zoom in that IT layer, we could see that we have sensors and actuators that are IP enabled, and we have certain processing done at the sensor level, and that sensor will communicate through TCP/IP using basically this TCP/IP protocol to store the data in the server and use the web services and the cloud that we all know about nowadays. So and there are horizontal communication between different layers. So you can have some IoT middleware where you plug the sensor and the sensor will communicate directly with your web server without you being overwhelmed with all the TCP/IP protocol that is going on between the two. So what are the challenges that we faced while implementing prototypes here? Is one of them is smart and reliable sensing. The quality of the analysis or the decision is going to be made will depend on the quality of the data and how you process it. We explored solutions such as smart doors, smart windows, etc. How could you model such complex systems so you can improve the reliability? Human behavior is also a very important part of it, because human will interact with building and we'd like to have that understanding of how the building is utilized by the occupants, and how can we model that behavior and provide a service that is appreciated by occupants. And obviously we're going to use machine learning to do that. So in terms of machine learning, what I'm showing here is really an application where we wanted to, for instance, estimate the attendance in building. How many people are utilizing a building? And here we're looking at commercial building, public building, etc. And we explored certain available infrastructure that we have. We know that we have Wi-Fi network. We know that the Wi-Fi basically has a ping that is interacting with everybody who enters the building, and we could, as an output, have I would say an estimate of the number of people inside the building. So what we have here is an experiment that we've done at the University of Houston, where we collected the number of users that pass by those buildings, and what you see on the top right graph is, on the x-axis is buildings. So we have buildings that are numbered, like 503 is a building and 516 is building, and this is the number of people occupying those buildings. That is one view, which is, for instance, a day view. And then if we take one building, and this is where I work, 547, which is the College of Technology, now we could track the number of people who come and occupy that building You could see that people start coming at 7, they leave around 8. This is the lunchtime. This is probably the afternoon session, and this is the evening session starting. So that gives us an indication of how building is being utilized. We used the recurrent neural network. We used LSTM to basically predict the number of people that will be inside the building, and the prediction we've done it at the 15-minute level and at the hour level. And the research question that we address in that project is how to predict the number of occupants using Wi-Fi beacons, which model will give us better accuracy, and can we basically improve that model and improve the computational performance of that model. How about other models like ARIMA and stuff like that? So we run that model, and we could now predict the number of people. Basically, this is what we have, the actual data and then the predicted data. And you could see this is kind of a day level of prediction. So you could see first day, second day, etc. We also, we could predict, study the comparison of different algorithms and their precision. This is another comparison also in terms of the access point level, the building level, and different algorithms. And we could see that the building level basically will give you better performance just because you're aggregating more data. Now, why do we need to do prediction? That comes back to the energy efficiency that we talked about. If we know how many people are within the building, and we know what time they come in and what time they leave, then we can adjust the settings. If I go back to this model, for instance, the building managers basically they set up certain temperature that start at 6 a.m. and it stays the same until say 9 or 10 p.m. and they don't take in consideration all this variation. And therefore, there is an opportunity to use this prediction basically to modulate the temperature inside the building at the day level and save more energy. And we could estimate that you could save even up to 15 to 20% of energy. We use that technique. Now, another problem that we worked on is really now, can we make that energy setting personalized? And if we do that, then we need to identify people. We know that there are multiple techniques. We could use, scanning card. We could use cameras and stuff like that. But the problem is cameras are intrusive, and scanning cards are cumbersome. People will not use it all the time. And we explored the idea of having what we call ultrasound sensing to do remote sensing without the user interacting or doing active things. So what we have here is implemented 3 ultrasound sensors at the door, and we measured this distance. And based on these distances, we could now predict that this person is so and so. So we implemented about 1, 2, 3, 4, 5 doors, doors at the building level and doors at the room level. And then we collected data for almost a month, and we take that data, we calibrate it, we do event recognition to make sure we have an event about somebody, we extract the features, and we do clustering to see if we can identify people. We also, to be able to recognize whether somebody is passing by, we have to have what we call a walk-in event, and we just make a simple decision that the height is more than 140 centimeters. Obviously, there are other techniques that you could use. And based on the feature we collected, we could extract the minimum, maximum, and mean height, the width, which is the width of a person, and based on that, we could calculate the girth, which is the circumference, time under the door, the distance between waist and hand, and maximum and minimum height, which is what we call the bounce. That is the processing. And then we use a DB scan to basically aggregate data, and we found out that that aggregation could give us an indication about the ID of that person. So every person has his or her own cluster. We run different verification in terms of how could we identify people with certain accuracy. And we have here if we use the height by itself or the height with the width and bounce and time and girth, etc. And we found that the girth along with the bounce and the width give us the highest precision. So we can identify somebody within 95%. This is basically the confusion matrix, and we could see which IDs are giving us issues. Excuse me. Now, using that data, we could even get more information that we were not looking for, which is, you know, can we find out whether a person is using a phone? And based on certain analysis, we could even determine that somebody is using the phone. Without using a phone, the person bounced back and forth in high waves, and then it goes abruptly. And what we were using is really time under the door. And if somebody is using the phone, you could see that there is the linear extrapolation of the data gives you basically this linear curve here. You could even tell whether somebody is carrying a backpack or not. And we did now we studied how many people we could identify using that technique, and we have here from 0 all the way to about, I think, 200, but the techniques will be very good around 100. The current literature of using non-intrusive technique, we're talking about, you know, 5 people, but we pushed the edge all the way to 100. And we did this because we introduced now the concept of activity or human activity or human behavior inside the building. If we take that in consideration, we can even improve this accuracy. So what next? I think dense sensing, including as many data as possible inside an environment is very important for us to do any type of smart environments. Using machine learning definitely is something that needs to be explored more, especially with the use now of yes. And then you have non-intrusiveness capability, smartness in the network, reliability, and autonomous building. And I would like to thank you for your attention. And I will be happy to answer any questions.
Thank you, Mr. Benhaddou, for this virtual talk. Now, we switch where the questions. Yasin, he asked for, can we consider smart building as a cyber physical system?
I mean, definitely, yes, you can consider them as a cyber physical system. And the cyber physical system and Internet of Things, they overlap. Excuse me. If you are going to implement a cyber physical system, you need the physical system, which is the building, and the cyber, which is the Internet of Things. And definitely now, cyber physical system and Internet of Things, they overlap. And yes, you can. A lot of research that has been undertaken under the cyber physical system are now also utilized for Internet of Things. The main difference is Internet of Things takes the or push the envelope further in terms of the application. You can now talk about, you know, the utilization of the environment, human and the physical interaction, physical system interaction, improve the business flow, stuff like that. So you're pushing the application to a wider space.
He asks also, what do you think about security and privacy issues in those systems?
Yes, security is really important. I didn't list it here, but definitely it is an important problem. So if you're communicating or if you're sending information about people, and you could see with as little information as an ultrasound distance sensor, you can tell who is going inside the building. It is very important now to do security. Data itself become power now because you could take the data and infer a lot of things out of it. So, and we know what's going on now with the social network data that people are using for different things and how it becomes very important to protect the data.
The other question is in the list. Thank you, Professor, for your presentation. I am interested on decision-making process methods. May you give more details about the clustering decision-making parts?
So decision making really start from your objective, right? And this refers back to, you know, if you sense data, why do you want to sense data, and what kind of decision you want to do? And so there is a general process that you can follow. Okay, I'm going to extract the data. I'm going to filter that data. I'm going to do something about it. So you're going to cluster it, or you're going to do some linear regression or whatever, or deep learning. Why you want to do that? So you need to start with asking the question, what type of decision you want to make? Is it a high-level decision? Is it low-level? When I say high-level, as human intelligence, low-level as turning on and off things. And what do I need to improve with that decision-making? So you really need to go specific to that question. And based on that, what data I need to make that decision. As human, we are intelligent, and without proper data, you cannot take the right decision. Same thing with these algorithms. We need to decide, okay, what data I need to have and how I'm gonna make that decision. And based on that, you start exploring the possibilities and the algorithm you're gonna do to make that decision. And that's what's become, you know, research is really exploring the what if and what parameters I need to tweak, stuff like that.
There is another question from Hannawi Sana. Thank you, sir, for your interesting presentation. I have a question concerning sharing data, or better say storing data in a distant server. Is this data will be secured, or it will be a public data which won't threaten the confidentiality of the people?
Yeah, it depends on what data you're having. If it is privacy data, then obviously you wanna secure it. If it is data that you would like to share with people, then you can do it public. There are a lot of data out there that is public data that you could download and work with. people anonymize it and share it with others so they can explore it and use it. The more data there, the more information you can get from it. There is a big project done in Singapore where they make all the data about their general power consumption of buildings available, and people are studying it and providing insight to the government. So they are utilizing researchers around the world to get insights about their data and learn from it. So again, it depends on the objective of the data. But in general, you want to start as secure and then decide whether you want to make it public or not.
Thank you a lot, Mr. Benhaddou, for this presentation.